I welcome you all to the session of engine system and performance, and today we shall discuss about the measurement of heat losses in engine, and then we shall solve one numerical problem to illustrate the concept of this particular topic that we have been discussing for the last two classes. If we recall, in our last class we have talked about heat balance, and we have seen that heat balance is nothing but the description of the disposition of the energy which is provided to the engine in the form of a fuel, So, you know that when fuel is supplied to the engine, essentially it is the supply of energy, because in the fuel itself chemical energy is remaining stored. Now, at the cost of that input energy, we get some power output at the output shaft of the engine, and we had seen in the last class that only 30% of the total energy which is supplied to the engine in the form of fuel is only available at the shaft as a as useful work, while remaining 70% of the total energy is either lost to the ambience or some part of the energy is used to run several auxiliary systems to overcome parasitic loads. And that means accounting of the energy that is supplied to the engine plus the output work or energy in the form of work which is available at the shaft plus energy loss or loss of energy is essentially the heat balance, or rather it can be described using heat balance. So, today we will see that measurement of heat losses in engine. Certainly, if we say that some part of the input energy is used to overcome the frictional losses, and also some part is transferred to the coolant, and some part is used to run several auxiliary systems, essentially for the parasitic loads. So, we have discussed about all these aspects in the previous class. So, today let us discuss about one particular method which is used to measure the loss of energy, which is again a substantial part of the total energy, and that energy is carried by the exhaust gases, and that energy is essentially lost, and that is supplied or that is transferred to the surroundings. So, today we shall take an effort to discuss one particular method by which the total energy which is lost from the engine by the exhaust gases that will be somehow measured quantitatively. So, if we go to the next slide, if we write that input energy to the engine that is 100%, and this is in the form of fuel, and we had seen out of this total energy roughly 30% of the total energy which is supplied So, total energy which is supplied is available at the output shaft of the engine. This energy is essentially in the form of what? In the form of useful work. So, you can understand from this particular block diagram that 70% almost 70% of the total energy cannot be used as useful work, and this 70% comprises heat loss or loss of enthalpy from with the exhaust gases, rather exhaust gases that is expelled from the cylinder, engine cylinder, carry some amount of enthalpy, that is loss of energy. Some part is used to overcome the frictional losses, some part is used to run the auxiliary systems for the parasitic loads. Even if it is a supercharged engine, then we have seen a part of the output work will be again used to run the compressor. Okay. So, essentially that 30% of the total energy which is supplied to the engine is available at the shaft, and out of this 30% energy a part will be again consumed by the compressor to supply compressed air or pressure air with high pressure having high density at the intake manifold, that will be made available at the intake manifold. So, now let us discuss about one particular method. So, you can understand out of this 70% substantial part or substantial amount is lost, substantial amount is lost to the ambience, and that is essentially loss of enthalpy carried by the exhaust gases. So, let me write here loss of enthalpy carried by the exhaust gases. So, had we taken an effort to utilize this enthalpy, which will otherwise will be carried by the exhaust gases and will be transferred to the surroundings, the efficiency of IC engine would have been even better, and I mean the efforts are now taken to utilize this amount, and you had seen one such avenue is to use turbocharging unit. So, the kinetic energy or enthalpy available with the stream of exhaust gases can be used to run a small turbine, which in turn will rotate a small compressor. So, now let us take an effort today to see a particular technique to measure this enthalpy which will be carried by the exhaust gases. So, for this is the schematic depiction, and this is essentially known as exhaust calorimeter. So, if I write here, so this is known as exhaust calorimeter. So, and this is used for the measurement of heat losses in engines. So, this is exhaust calorimeter. Okay. Now, in this we can see that this exhaust calorimeter is essentially a heat exchanger, and if you look at this schematic carefully, you can see that there is a tube through which exhaust gases flow, and in this particular casing, this system, water is or cold water is circulated over the tube, so that certain amount of heat can be taken by this water and that is water out. So, essentially this is a heat exchanger, and you can say this is a cross flow type heat exchanger, because you know that gas stream is taking place from left to right. So, this is the gas flow direction, while the water direction is something like this. So, this is water flow and this is gas flow. Okay. So, we had studied in our heat transfer course that parallel flow, you know, heat exchanger, counter flow heat exchanger, again cross flow heat exchanger. So, the idea is it is exactly not you know what I am telling cross flow, but to some extent you can consider this is a counter flow, because gas is you know flowing, or exhaust gases flow from left to right, while water will pass, or water is allowed to flow past the tube, and either it can flow opposite to the direction of gas flow, or it is just crossing the gas stream. So, in this case you know what is done, this exhaust calorimeter is essentially a heat exchanger. So, exhaust calorimeter, it is essentially a heat exchanger, and in this heat exchanger there are two different streams. One is stream of exhaust gases and water stream. So, these two different you know fluids is allowed to flow through this particular device, and in the course of their flow through this device they exchange heat, and the main idea or sole idea is to take off certain amount of heat from the flowing gas stream by the water, and the water temperature at the outlet will be little higher. But the question is you know that here in this exhaust calorimeter care must be taken so that the gas temperature can be reduced or it can be moderately cooled. So, gas is cooled at a moderate temperature. In other words, I can say the flow of or flow rate of water which will be circulated through this particular unit is regulated such that the temperature of gas at the outlet does not fall below 60 degree. So, let me write here and then I will tell why it is so. So, this is one thing. Second thing is, as I was talking about, that the flow you know the rate of or flow rate of water, certainly this is cooling water, right. So, the flow rate of cooling water is regulated such that the temperature of the gases at the exit of the calorimeter does not fall below 60 degrees Celsius. So, this is very important. That means, the gas is moderately cooled, and if we need to ensure that the gas temperature can be cooled moderately, we need to control the flow rate of water so as to maintain the temperature of the gases at the exit of this calorimeter will be always above 60 degree, because the dew point of the gas is 60 degree. So, certainly it is not advisable to go the temperature of the gases at the exit of the calorimeter below 60 degree. Okay. So, if I go to the next line, so the reason is the dew point of the dew point temperature, to be precise, dew point temperature I should write dew point temperature of the gases is 60 degree Celsius approximately. So, this is approximately. So, that is why it is always ensured that the temperature of the gases at the exit of the calorimeter should not fall below 60 degree, and that is why the control over the mass flow rate of water or flow rate of water will would be there. Okay. So, now if we go back to the previous slide, if we assume that mass flow rate of water is, so if I write here, so mass flow rate of water is m dot w and gas flow through this tube is m dot g, then we can have some heat balance or energy balance of the exhaust calorimeter for this typical circuit. Okay. So, if we write here the energy balance or heat balance, whatever it is, energy balance of the exhaust calorimeter. Right. So, if we take an effort to have this, then we can write m dot g, that is mass flow rate of gas leaving the calorimeter into Cpg into Tg in minus Tg out. So, if we go back to the previous slide, let me write here. So, if the temperature of the gas at the inlet is Tg in and temperature of the gas at the exit of the calorimeter is Tg out, and then we can write that the amount of energy will be given or will be released by the gas stream is nothing but m dot g into Cpg into Tg in minus Tg naught or Tgo. So, you have studied this, is very simple. Now, the question is this fellow, if I write here Cp, had we considered the gas to be a calorically perfect gas, we could have considered Cp is constant, but essentially the temperature of the exhaust gases is so high that Cp will vary. Cp is a that the specific heat at constant pressure. So, it is strongly dependent on the temperature. So, Cpg, which strongly depends on the temperature, right, and that too it is not a particular gas, rather gas mixture. So, we have to take average Cp, which is, the average value of Cp should be taken into account while we are going to calculate this essentially analytically. So, the Cp is function of temperature and that too this is a gas mixture. Okay. So, this is the amount of energy that will be released by the gas stream and that should be equal to. So, if I write here, so the amount of energy is released by the gas stream. So, that is the flowing gas stream, and this is this quantity. Okay. So, if I now write, so the amount of energy that will be released by the gas will be taken away by the water stream. So, that is m dot W into Cp W into T W in minus T W out. So, if we assume that the temperature of the cooling water is T W in and temperature of the coolant at the exit of the calorimeter is T W O, then this is the energy balance. Very simple method. So, from this equation we can write that m dot G Cp G that equal to, rather I can erase this part, equal to m dot W Cp W T W in minus T W out divided by T G in minus T G out. Okay. So, this is the expression. Now, this quantity which is the product of mass flow rate of gas and the specific heat of the gas stream can be expressed by this quantity. So, try to look at the quantity which is there on the right hand side of this equation here. So, we know mass flow rate of water which can be measured, the specific heat of water, water temperature will be something which we can assume that is not going to alter the specific heat, that can be known a priori. We can measure temperature of the cooling water at the inlet, and certainly we can measure temperature of the cooling water at the outlet, and also we can measure gas temperature at the inlet and gas temperature at the outlet. So, measuring all these quantities we can have the information about this, that is m dot G and multiplied with Cpg. So, if we go to the previous slide here, we assume that temperature of the water at the outlet is T W O, while this is T W in. So, this is the expression. Now, if we go to the next slide, so this is the amount of the product of the mass of the gas and specific heat can be measured. So, certainly measuring this we can have some estimate of the heat that will be taken by the exhaust gases, and this amount of energy in the form of heat will be released by the gases in the surroundings. So, essentially this is the loss of enthalpy. Now, if you would like to take an effort, the total heat carried. So, if I take an effort to write, so total heat that will be carried by the exhaust gas, carried by the exhaust gas can be now measured, that equal to m dot G Cpg that we have measured from this equation. Measuring all this quantity we can have an estimate of this, that is the product of gas mass flow rate of gas and specific heat. So, this is known. Then we also know T G in minus T ambience. So, essentially this is the total amount of energy that will be lost to the surroundings, and this much amount of energy in the form of heat will be carried away by the exhaust gases, because we know this quantity and we also know the ambient temperature, and already we have estimated this quantity from the equation that we had written in the previous slide. So, this is the thing. Now, the question is, this is one method of calculating heat or heat loss or energy loss, and that energy will be transferred to the surroundings. Essentially, this much amount of energy will be carried away by the exhaust gases. So, there is another method which can also be used to calculate loss of enthalpy, rather the enthalpy that will be carried away by the exhaust gases. So, if I write here just for 1 minute, so we can write that enthalpy of the exhaust gases, because this is the enthalpy which we cannot use. Had we taken an effort to use this much enthalpy, then certainly we would have enhanced the efficiency of the engine, and engine performance would have been even more better. So, enthalpy of the exhaust gases can be determined. I am writing this step using the polynomial function, using a polynomial function. Okay. Now, this polynomial function defines the enthalpy of the constituents or components of the exhaust gases, right. So, that means either we can use exhaust calorimeter to estimate the loss of energy, otherwise we can define mathematically a polynomial function, and that polynomial function can be used to measure the enthalpy of the exhaust gases, because the polynomial function defines the enthalpy of the constituent or components of the exhaust gases. But the problem associated with this particular method is we need to know about all the constituent components of the exhaust gases precisely, and that to the temperature of the exhaust gases. So, this is one method of measuring enthalpy, and so if I write here just for the sake of completeness, right. So, this requires one is knowledge of the temperature and composition of the exhaust gases. I should say you need to know very precise information about all these 2 points, that is temperature and composition of the exhaust gases. So, now let us consider, instead of defining using a polynomial function which defines the enthalpy of the constituents of the gases, exhaust gases, let us now consider one particular example wherein we can use property tables. So, another method could be the use of property tables, and using property table we can calculate enthalpy, absolute molar enthalpy of the gas mixture, and let us take an effort to discuss that particular method by taking or illustrating a particular example. So, if we go to the next slide. Okay. So, this is the problem statement. Let me read the problem statement first, then we shall try to see the solution procedure. So, in this problem statement it is given, compute the enthalpy of gas mixture at 1000 Kelvin having the following constituents and mole fraction. So, in the exhaust gas mixture or gas stream, there are CO2, H2O, N2, CO and H2. So, the constituent components are carbon dioxide, H2O, that is certainly moisture content, but it would be in the superheated state, then N2, then carbon monoxide and hydrogen. So, knowing all these components and that too their mole fraction, we can estimate enthalpy of gas mixture which is at 1000 Kelvin. Now, let us use the property table to estimate the enthalpy of the gas mixture. Let us now solve this problem. So, for this problem what we can do? We can first form the gas property tables. So, this is gas property table. So, we have a few species, then we have mole fraction that is also given. We need to know two important thermodynamic properties, as such two important concept of enthalpy to estimate the total enthalpy of the gas mixture. So, let me write here. So, this is species and this is mole fraction yi. So, yi is the mole fraction of ith species, and then here we need to know about the enthalpy of formation, that is H bar F at reference condition 298, and the units should be, and then we have to calculate the sensible enthalpy change of species. So, this is delta S I bar. So, here this H F which is at the reference state, see the overbar symbol is used to here we have used overbar symbol. So, this is the enthalpy of formation at reference temperature say 25 degrees Celsius, okay. And this delta H S I. So, this is again this is I should write bar. So, this is the sensible enthalpy change of species I, sensible enthalpy change of species I or ith species. So, ideally I should write F I (298), because enthalpy of formation at reference temperature. So, now in the problem statement, mole fraction of, there are 5 different components CO2, H2O, N2, CO and H2. So, if I write the first species, if I write CO2, so mole fraction is given 0.109 and the information about the enthalpy of formation at reference state is also given. So, this is minus 393,522 unit. So, unit of these two is kilojoule per mole. So, kilojoule per kilomole. So, unit of these two quantities, that is enthalpy of formation at reference state of species I or ith species, and this is the sensible enthalpy change of species I, unit is kilojoule per kilomole. So, this is 522 and this is also given 33397. So, all these are given in the table itself. So, if we write similarly the table for this next component, that is H2O. So, it is mole fraction is 1 to 1, that is given, and this is minus 241 826, this is 30190. Similarly, we can write for N2. So, for N2 it is 0.694, that is the mole fraction, then it is 0, this is also 0, no, so this is not 0, this is 21463. The sensible enthalpy of change of species cannot be 0. So, the next one is CO, mole fraction is 0.0283, and this is minus 110527, and this is 21686, and then final constituent is H2 hydrogen, mole fraction is 0.0455, that is given, this is 0, that is the enthalpy of formation at absolute at reference state, and this is 20663. So, knowing this gas table, we can estimate the absolute or molar absolute enthalpy, that is H T equal to I can write summation of I equal to 1 to 5, because there are 5 species, y I into H bar F, that is enthalpy of formation at reference state, plus this delta H S I. So, this is delta H S and this is for I. So, if we calculate, so essentially try to understand, we have enthalpy of formation at reference state from the gas table, we have information about the sensible enthalpy change of species I from the gas table, we know the mole fraction because this is kilojoule per kilomole, and from there we can have molar absolute enthalpy of the gas mixture, which is which is having components like CO, moisture content, which must be in the superheated state at high temperature, nitrogen, carbon monoxide and hydrogen. In this context, so this is the example I had I have given you. Perhaps this concept is very much used in the area of combustion science. So, let me tell you one thing, for any gas mixture, in particular chemically reacting gases, for any chemically reacting gas or any gas mixture, concept of absolute entropy is very much needed, and we are trying to figure out the molar absolute enthalpy. So, concept of absolute enthalpy is very much needed for the chemically reacting gas or gas mixture, and which is this absolute enthalpy of a chemically reacting gas or gas mixture is or has two components. One is associated with the energy of bond, chemical bond rather, and that is nothing but the enthalpy of formation. So, we have enthalpy of formation HF at reference state 298. So, this is essentially the signature of energy associated with the chemical bond, and another one is the change in enthalpy, rather enthalpy due to temperature. So, change in temperature, right. So, we know H is equal to Cp into T or dH equal to Cp dt, right, that we have studied in our thermodynamics. So, the energy or enthalpy associated with temperature change, that is nothing but this. In fact, if I write here this delta H S I is nothing but H minus H 298. So, this is the sensible enthalpy change of species I. So, this is one method by which we also can measure the absolute enthalpy of the gas stream that will be expelled or that is expelled from the engine cylinder into the ambience. Because today we wanted to discuss about the loss of energy into the ambience, and that loss of energy is essentially due to the removal of exhaust gases. So, now let us solve one numerical problem. Second problem, just to illustrate the first method we have discussed in today's class. So, if we go to the problem statement, so this is the problem statement. In this problem, that it is given, let me read the problem statement first. The following data is given for a 4-cylinder 4-stroke oil engine. So, essentially you can understand the engine is 4-cylinder and 4-stroke cycle oil engine. So, here it is given for the fuel compositions are hydrogen 11% by mass and the rest is carbon. So, essentially you know that fuel is basically hydrocarbon. So, family of hydrocarbons rather. So, in this fuel particularly we have hydrogen is 11% by mass while the rest is carbon. Ambient temperature is given 25 degrees Celsius, engine exhaust temperature is 325 degrees Celsius, average specific heat for the exhaust gases is given. As I was talking about, specific heat strongly depends on temperature, hence while you are trying to estimate the enthalpy of the exhaust gas, it is very difficult, or gas mixture, it is very difficult to use a constant Cp, rather we have to take average Cp. So, average specific heat of exhaust gas is given, air consumption and fuel flow rate are 32 kg per minute and 1.3 kg per minute. So, if we try to recall the exhaust calorimeter, there are two different streams, one is the stream of exhaust gas and another one is the water stream. So, in this particular problem given air consumption and fuel flow rate. So, for the engine operation we need to supply air and also need to supply fuel, because fuel is the energy that is supplied to the engine, and calculate the mass of steam in the exhaust. So, basically try to understand, we have to calculate m dot g, the mass of steam in the exhaust. So, basically it is not m dot g, rather m dot moisture. So, it is m dot H2, because that what moisture would be in the superheated state. Calculate the heat loss with the dry exhaust gases as well as heat carried by the steam, because steam will carry certain amount of heat, and also you have to calculate the heat loss with the dry exhaust gas. So, let us solve this problem and then you will understand. So, if we solve the problem, so from the data we can understand total mass of exhaust gas, total mass of the exhaust gases equal to how much? It is given 32 kg per minute and 1.3 kg per minute respectively. So, exhaust gas will be essentially the combination of air plus fuel. So, it is 32 plus 1.3. So, this is kg per minute and this is 33.3 kg per minute. Okay, so, this is the mass of air. Now, kg of hydrogen per kg of fuel. So, we have to calculate now kg of hydrogen per kg of fuel, that we can estimate because it is given 11% by mass. Okay. So, that is given, and so that is 11%. So, it is 0.11. Okay. So, it is given fuel, hydrogen is 11% by mass. So, also kg of hydrogen per minute. So, this is kg of hydrogen per kg of fuel, and we can see total. So, we can from here we can write also kg of hydrogen input per minute. So, kg of hydrogen per kg of fuel is 0.11 by mass. So, kg of hydrogen input per minute should be equal to, because we need to supply that exhaust gas. So, it is essentially 0.11 into flow rate, fuel flow rate is 1.3 kg per minute. So, 1.3. So, this is kg per minute. So, this is that if we supply 1 kg of fuel, then the kg of hydrogen is 0.11, that we can see from the previous line. That means, we need to supply 1.3 kg of fuel per minute. So, essentially kg of hydrogen input per minute should be equal to 0.11 into 1.3 kg per minute. So, this is the value. So, now let us write the reaction equation. So, if we write the reaction equation for H2, twice H2 plus O2 equal to twice H2O. From this equation we can tell that kg of moisture per kg of hydrogen. So, kg of moisture per kg of hydrogen is essentially 9, that we can see, right. So, that we can understand from this reaction, very simple reaction that you have studied in your 10+2 chemistry course. That means, from this equation we can calculate kg of moisture per minute, that equal to 9 into 0.11 into 1.3. So, this is the per minute kg of moisture we are getting. So, this is one answer for this problem. So, if we go back to the problem statement, it is given calculate the mass of steam in the exhaust. So, water content, the moisture content in the exhaust, because exhaust temperature is given as 325 degrees Celsius. So, at that temperature H2O will be certainly in the superheated state, because pressure is also given, because typically if it is atmospheric pressure or even less than that. Even at atmospheric pressure water boils at 99.99 degrees Celsius temperature. So, certainly at 325 degrees Celsius temperature, even if the pressure is atmospheric pressure, it would be in the superheated state. Okay. So, now next try to calculate mass flow rate of dry exhaust. So, from here we can calculate mass flow rate of dry exhaust. So, total mass flow rate, if we can recall, we had calculated in the previous slide 33.3 kg per minute. So, this contains moisture as well. So, if we deduct this amount, so 33.3 minus 9 into 0.11 into 1.3. So, this is the amount, that is kg per minute. Okay. So, exhaust gas, what we can see from this analysis, exhaust gas is having dry gas plus moisture, is not it. So, moisture content we have calculated, if we deduct this amount from the total mass, then we can have mass flow rate of the dry exhaust. Now, heat losses associated with them are to be calculated. So, this what I can write, exhaust gas or exhaust gases, I can say it has two components, one is dry gas or another one is moisture content. So, we have to calculate heat losses associated with these two streams. Okay. So, the exhaust gas is comprised of dry gas and moisture. So, we have to calculate heat loss or heat losses associated with these two streams. Okay. Now, if we go to the next slide, we can certainly write heat loss to the dry gas, that equal to m dot dry gas Cp dry gas into Tg minus T ambient. Okay. So, m dot Dg, that already you have calculated 33.3 minus. So, if I erase this part, so it is minus, if we go 0.11 into 1.3 into 9 into, it is given Cpg. If we go to the problem statement, it is given average specific heat for the exhaust gas is 1.2 kilojoule per kg Kelvin, while engine exhaust temperature is 325, that is Tg is 325. So, if I write here into 325 minus ambient temperature is 25, that is given. So, if we calculate it, this is the total amount of heat loss to the dry gas. Okay. Now, if we assume that the dry gas is supplied to the engine and whatever moisture content we are getting in the exhaust gas is solely due to combustion. So, that means the air which is supplied to the engine does not contain any moisture. So, moisture content in the exhaust gas is solely due to the combustion. If we assume this, so if we assume here that the moisture in the exhaust gas or exhaust gases is solely due to combustion of hydrogen. So, this is the assumptions we are going to consider. Certainly, that air which is being supplied to the engine, if it is supercharged or turbocharged engine, no moisture content will be there, but okay, we are assuming this. If it is the case and you try to understand, this is the temperature of the hot gas, that is the hot gas or hot gases leaving the cylinder, and at that temperature whatever moisture will be produced because of the combustion of H2 hydrogen, what moisture will be in the superheated state, right. So, that we can understand. So, if we go to the next slide, assume that at 325 degrees Celsius, steam in the exhaust gas exists in the superheated state, okay, and it is given that the partial pressure of steam in the exhaust is assumed to be 0.1 bar. 0.1 bar means 0.01 megapascal, okay, that you know. So, 1 bar equal to 100 kilopascal. So, 0.1 bar equal to 10 kilopascal, and that is nothing but 0.01 megapascal. Okay. So, if we use steam table, probably you know very well. If you use steam table, you can try on your own even. So, we know the partial pressure of moisture or steam, certainly it is not moisture, partial pressure of moisture, that would be in the superheated steam in the exhaust. We know the pressure 0.01 MPa, and we know the temperature. So, this is the pressure and this is the temperature, that is 325 degrees Celsius. If we consult with steam table, we will find that the steam will be in the superheated state. From there we can calculate enthalpy, right. Certainly, you know, if we write here, you know, this is the superheated region, and from there we can calculate, just for your information, that you will get 400, because our temperature is 325. Essentially, we have to measure enthalpy corresponding to 325. So, if we take these two temperature in the steam table, 400 and 300, because 325 is in between these two, and at, if we look at superheated table corresponding these two values, we will be getting 3280 kilojoule per kg minus this H we have to calculate at 325. This is 3280 minus 3076.7. Okay. So, from there if we calculate, certainly enthalpy is coming as 3127.525 kilojoule per kg. So, that means, if we go back to the previous slide wherein problem statement is given, we can see that we have to calculate the heat loss with dry exhaust gas as well as heat carried by the steam. So, you know, calculating enthalpy of the steam in the exhaust gas, we can have some estimate, and we can have, you know, ambient temperature is 25 degrees Celsius, pressure of the steam is 0.01 megapascal, right. So, at this temperature we can have, you know, saturation enthalpy. So, this is saturation enthalpy equal to 104.83 kilojoule per kg. So, this is the saturation enthalpy corresponding to this temperature 25 degree Celsius temperature, again we will be getting it from the steam table. Now, what we can see that we could calculate the enthalpy of the, you know, steam which will be in the superheated, because here we wanted to have heat losses associated with these two streams must be calculated, and we have the enthalpy of steam which is, or enthalpy of the moisture which will be in the superheated, you know, state with the exhaust gas, and if we know the saturation enthalpy corresponding to 25 degree Celsius temperature at the surroundings or ambience. So, this change in enthalpy is essentially loss that we can calculate, and loss due to dry gas that already we have calculated. So, by solving this problem, essentially we have tried to illustrate the concept that we have learned today, that, you know, estimation of heat loss from the engine. So, if I would like to summarize our today's class, then we can say we have discussed about the measurement methods of energy loss or heat loss from the engine. We have discussed about exhaust calorimeter. Thereafter, we have solved two numerical problems. One problem is essentially to illustrate the use of or illustrate the concept of using gas table to calculate the loss of enthalpy, which is essentially the loss of energy. And finally, we have solved one numerical problem to illustrate the method that we have discussed in today's class. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.